is Yuli, and we'll talk about integrable systems on the dual of nilpotent subalgebras and T-Poisson cluster structures. Thanks.
Yeah, thank you. Thanks a lot for the introduction, and thank you to the organizers for having me. I'm sorry that I can't be there with you for visa reasons, but hopefully I'll see everybody soon, maybe in the summer. Okay, so this is based on joint work with Yanpeng Li and Jianhua Lu. My plan for today is as follows. So first, I'll give you some motivations. So basically, this is to explain what a T-leaf is, and then I'll construct our integrable system using representation theory techniques, and then I'll reinterpret our integral system using class algebras, and time permitting, I'll also tell you how to think about our integrable system in terms of the T-Poisson Fabian on Broussard cells. Okay, so let's start with the motivation. So I'll let T be a torus, and for me, everything is algebraic and over the complex numbers. I make T act on a Poisson manifold or smooth Poisson variety y comma pi by Poisson automorphisms. And then by a T-leaf, I mean a subvariety of y of the form, so union over elements small t of the torus of T acting on S, where S is a symplectic leaf. So you just take the T orbit of a symplectic leaf, and that's called a T-leaf. And then there's a folklore due to Gechtmann, Shapiro, and Weinstein, which says that on the coordinate ring of every T-leaf, there should be a class algebra structure which is compatible with both the T action and the Poisson structure. So what does that mean? So at the very least, compatibility here should mean the following. So we can find some local coordinate charts, y1 through yn, on the T-leaf, which we will refer to as a T-chart, such that each of the coordinate function is a T eigenfunction. This is compatibility with the T action. And then moreover, the coordinate functions are log canonical in the sense that if you take the Poisson bracket of yi with yj, you are going to get some constant times yi yj. Okay, and we have examples of a lot of examples of T-leaves, for example, on the double Broussard cells, reduced double Broussard cells, Samuelson charts, blah, blah, blah. And these are examples on which there are known compatible cluster structures. But then here's an interesting remark. So most of the known examples of T-leaves on which we do have a compatible cluster structure have to do with the standard Poisson structure on the semi-simple group G. However, the Kirillov-Kostin Poisson structure, which I guess intuitively is much simpler, very rarely appears in this business. So what I'm going to do today is kind of try to bring the Kirillov-Kostin Poisson structure into this picture. So I need to fix some notations. So this math frac G is a semi-simple Lie algebra, and I fix a triangular decomposition of n plus h plus n minus. And from now on, my torus T will be a Cartan subgroup integrating H. And then naturally T acts on the dual space of n minus by the coadjoint action. And then there's an interesting fact due to constant, which is that if you take the Kirillov-Kostin Poisson structure on the dual space of n minus, this actually contains an open dense T-leaf. Okay, and moreover, this open dense T-leaf can be described in a very explicit way using his notion of cascade of roots. Okay, so then the morally n minus star is very close to being a T-leaf. So the natural question to ask is that is there a compatible cluster structure on n minus star? Okay, so what we have done is that we have constructed an integrable system on n minus star equipped with the Kirchhoff constant Poisson structure. And moreover, each function in our integrable system is indeed a T eigenfunction. Okay, so then in some sense, we have constructed half of a T chart. So what do I mean by this? So first of all, so remember in our compatibility conditions, so each coordinate function has to be a T eigenfunction. So functions in our integrable system are indeed T eigenfunctions. And then the second condition says that the functions have to be log canonical, but integral systems consist of Poisson commuting functions. So if you take the Poisson bracket, you just get 0. So that's the case where this omega ij is 0. Okay, and then if you are on a symplectic manifold, then the number of functions on in an integral system is half the dimension of the manifold. And if you more general, if you are on a Poisson manifold, then you just insert the Casimirs. So essentially the number of functions in an integral system on a Poisson manifold is half the dimension of the Poisson manifold. And this is what I mean when I said that we constructed half of a T chart. Okay. Are there any questions so far about the motivation? All right. So then I'll tell you how we constructed this integral system. So first of all, this is inspired by a construction due to Constant, Liebsman, and Wolf. So we start with a dominant integral weight lambda, and then I write V lambda for the highest weight lambda representation, V lambda star is the dual representation. And then for any Val group element small w, I introduce the following vectors. So first, this B sub W acting on lambda is a weight vector inside the representation V lambda of weight W acting on lambda. So it's an extremal weight vector. And then Z sub negative lambda is the lowest weight vector of the dual representation. So it's of weight negative lambda and it's dual to the highest weight representation, highest weight vector of V lambda. Okay, and then using these, I can construct a linear functional on the universal enveloping algebra UG of G in the following way. So this functional is denoted by F sub W comma lambda. What it does is that it sends an element X of the universal enveloping algebra to the following. You first make X act on this extremal weight vector. That's something living inside the representation V lambda, and then you pair that with this dual vector. Okay, and in general, if we have a Lie algebra S and a linear functional G on the universal enveloping algebra of S, we can define its codegree to be the minimal integer C, such that when you restrict the linear functional to the degree less than or equal to C part of the universal enveloping algebra is non-zero. Where degree less than or equal to C just means degree less than or equal to C with respect to the PBW filtration. Okay, so then we can apply this notion to our setting to our F sub W comma lambda. We denote this codegree by CD sub W comma lambda. And then one more standard definition from representation theory. If you have a Val group element small w, then its inversion set is the set of all those positive roots alpha, such that when you apply W inverse to alpha, you get a negative root. And then with this, I can define a Lie subalgebra N sub W of N. It's just a direct sum over all those root spaces G alpha, where alpha runs over the inversion set of W. And then once I've defined these, I have the following big commutative diagram. So I can start with the Lie algebra NW and take the degree less than or equal to CD part of the universal enveloping algebra. Whatever that is a subspace of the universal enveloping algebra, which in turn is a subalgebra of UG. And on UG, I can apply my linear functional f sub w comma lambda that we constructed above. And then remember, from the symmetric algebra to the universal enveloping algebra, we always have the symmetrization map. Okay, so then we precompose with the symmetrization map, and the result we get is denoted by this. So f sub parentheses w comma lambda. Okay, so this is the first time you see this this construction. It might look complicated or maybe even scary, but whatever it is an element of the Dura space of the CD's sim power of NW, which we identify with the CD's sim power of NW star, which are just homogeneous polynomials of degree CD on NW, which sits inside the coordinate ring of NW. And then via the killing form, I identify NW with the Dura space of the opposite version of NW, so NW minus star. So then this line that we constructed using this complicated diagram now can be thought of as a polynomial on NW minus star. Okay, but I can also think of it as a polynomial on N minus star because N and W both have root space decompositions, and so NW in N has a preferred complement. All right, so the way I'm going to apply this construction is as follows. So I let W naught. Oh, sorry, is there a question or something? Okay.
You're fine.
Oh, yeah, sorry, I heard something, so I thought that was a question. But okay. So I let W naught be the longest element of the vowel group, and I fix the reduced word SI1 through SI capital N. And then for any integer j between 1 and n, I just do the usual thing. I put wj to be SI1 times ... times Sij. So you just truncate this word at place j, and then take the product of the first j simple reflections, and then I'll have a vowel group element wj, and I'll also have a fundamental weight omega ij, corresponding to the fundamental root alpha ij. So then I can apply my construction above to this vowel group element and this integral dominant weight. So then I get a linear functional f sub wj comma omega ij on UG, and for simplicity, I'll just write f sub j for that. Okay, and then this f sub j as a linear functional on the universal enveloping algebra of G has a codegree, and that codegree is denoted by the CD sub j. Okay, and then I can apply this big diagram. So then I get a polynomial. This polynomial will be denoted by f sub parentheses j. This again is a polynomial on wj minus star, but again I can think of it as a polynomial on n minus star. Okay, so then I can state our main theorem, which says that any maximal algebraically independent subset of the set f parentheses 1 through f parentheses n is an integrable system on n minus star equipped with the Kirchhoff constant Poisson structure. Okay, so my construction is probably a bit hard to understand. So let me give you an example. So assume that we are in type A5, and for the reduced word for the longest element, I just choose this very nice one. So S1 through S5, and then S1 through S5, and then S1 through S4, S1 through S3, S1, S2, and then S1. Okay, so then we compute, I'll only compute one of the functions in our construction. So I'll compute F1. So then for this, remember that I will need this value group element W1, and also need this omega I1. The W1 by definition is just SI1, and SI1, so the first reflection is just S1. Okay, and then omega I1 is the fundamental weight corresponding to omega to S1, so it's just the first fundamental weight. And therefore, the representation that we consider is the first fundamental representation of SL6. So it's the vector space C6 acted on by SL6 in the usual way, just left multiplication. And then I identify the dual representation with C6 just by using the usual inner product. And then it's easy to see that the lowest weight the lowest weight vector inside C6 is just E1. So if E1 through E6 are the natural basis for C6, then E1 via the usual inner product is dual to E1. So this E1 is the lowest weight vector. And then this vector V sub W acting on lambda is E2. This you can check at home very easily. Okay, so then our linear functional F1 on the universal enveloping algebra of SL6 sends an element X to X acting on E2 and then paired with E1, so inner product with E1. Okay, then the co-degree of this functional is equal to 1 because, so if X were in degree less than or equal to 0 part of the universal enveloping algebra, namely X were just a scalar, then X acting on E2 is a multiple of E2, then E1 paired with a multiple of E2 is 0. But if X is of degree less than or equal to 1, then we can take, for example, then we can take this X. Okay, when you multiply X with E2, you get the second column, and the inner product with E1, you get the first entry of the second column. So you just get this 1 here. So so that's why F1 on this element X is equal to 1. So it's non-zero. Therefore, the co-degree of F1 is equal to 1. So then when you apply this big diagram, the polynomial F sub parentheses 1 you get is of degree 1 because co-degree is 1. And what this degree 1 polynomial does to such an element of the maximum nilpotent is that it just takes the entry in this box, the entry in the first row and second column. Okay, so that's a very simple example of what our construction does. Then using, well, and then in this example at least you can try to compute F2, F3, blah blah blah, all the way up to F15, and then you will realize that for this example there are only 9 functions in our collection F1 through F15. And they are as follows. So first we have all the entries in the first row, and then we also have the minors of the 2x2 blocks that I draw in the picture. Sorry, the determinant of the 2x2 submatrices I draw in the picture, and also the determinant of this very big 3x3 submatrix. Okay, so there are 5 plus 3 plus 1, 9 functions. Remember that n minus star in type A5 is 15-dimensional. Its maximal dimensional symplectic leaf are all 12 dimensional. So then there are 3 Casimirs, right? So then an integrable system should consist of 6 functions on the leaves and plus 3 Casimirs. So all together you have 6 plus 9, which equals 6 plus 3, which equals 9 functions. Okay, so then how do we think about our integral system using classical algebra? So first I introduce the Bott-Samuelson coordinates on the open Broussard cell. So it's a function going from C to the nth power to the open Broussard cell, defined in this way. This is an isomorphism of varieties. And this isomorphism identifies the coordinate ring of the open Broussard cell with the polynomial ring in x1 through xn. And what is interesting is that, so first of all, the open Broussard cell contains an open density leaf, and the Bott-Samuelson coordinates make the open Broussard cell into what is called a symmetric Poisson CGL extension. This is proved by Lu, and it's also in my work. Therefore, by the work of Goodall and Yakimov, the open Broussard cell has a cluster algebra structure. And what plays an important role in this cluster algebra structure are the following functions, yj. Okay, so I probably won't go into the details of the definition of the yj's, but if you know the theory, I mean, these yj's are just the homogeneous Poisson primes. Okay, so then I would like to relate on these yj's to our functions above, and here's what we do. So again, for each integer j between 1 and n, my reduced word for the longest element of the group, gives me an enumeration of positive roots like this. So I define lambda j to be si1 dot sij minus 1 acting on alpha ij. So that's a positive root, and lambda 1 through lambda capital N is actually the set of all positive roots. And then for each positive root, I choose a corresponding root vector, e sub lambda j, and then that will give me a vector space isomorphism from C to the N to the algebra N, sending the tuple x1 through xn to x1 times e lambda 1 plus dot dot dot. Now in this way, the coordinate ring of n minus star, which I identify via the Killing form with the coordinate ring of n, is identified with the coordinate ring of C to the N, which is just polynomials in the variables x1 through xn. Therefore, the functions f1, f parentheses 1 through f parentheses capital N on n minus star can be thought of as polynomials in the variables x1 through xn. Okay, so then here's our next interesting result. So for these homogeneous Poisson primes, these are polynomials in x1 through xn, so you can take their lowest degree terms. Okay, these lowest degree terms turns out to be the same as our functions. Okay, so then I'll maybe use the last minute to explain why these functions, why our functions Poisson commute. All right, so in the Bott-Samuelson coordinates, one can easily show that the standard Poisson structure is the Kirchhoff-Colson Poisson structure plus some higher order terms. So then we use the fact that the yi's are log canonical with respect to the standard Poisson structure. So we have this equality, and we compute the lowest degree terms of both sides. So on the left-hand side, obviously, the lowest degree term comes from pi kk. So you just take the Kirchhoff-Coulson Poisson structure bracket of the lowest degree terms of yi and yj. But notice that because the Kirchhoff-Coulson Poisson structure is of degree -1, so the degree of this Poisson bracket is the degree of yi low plus the degree of yj low -1. But then the lowest degree term of the right hand side is just omega ij times yi low times yj low, whose degree is that. Okay, so then this line on the left hand side is too small. Its degree is too small, so it must be 0 for the equality to hold. Okay, yeah, so my time is up. Yeah, let me just remark that this whole thing works for any NW minus, not just for the longest word. Okay, I'll stop here. Thank you.
So, are there questions? Question from the line?
No questions on Zoom.
No questions on Zoom. So I think we can thank Yuli again.
Thank you.